Hello, and welcome back to QuickType Inside Out episode 4, where we are implementing a renderer for C++, so C++ support for QuickType. If you recall from the last episode, we implemented outputting very basic structs that weren't really structs yet. But we ran into a bug, and I said I was going to fix it, and I did that, and I actually even did that refactoring that I said I was supposed to do, which is why we're getting this error here now. Namely, I put the name style into the namer. So now, as you can see, the namer doesn't want as its argument whether to produce an uppercase or lowercase character, but it just wants the name style, and whether the name is going to end up uppercase or lowercase is the responsibility of the name style. So we're going to give this name style to the namer, and now there's another change, namely the convenience renderer doesn't require us to implement these two methods anymore, or I should put it in other words, these two methods don't even exist anymore. But the reason for that being is that we have these namers for the types and the properties, right? So I'm going to move those here. And these already contain name styles. So these are superfluous. There's no point in having them. So they go away. Now you might ask, why is there still a name style for the top level name? The reason for that is that, as I said, the names for the top level types are usually given by the user, and we just assume that there's no collisions. And so we don't put them through a namer. So they will never be othered. Like if you give a top level name of foo, it's never going to come out purple foo, right? It would be very bad if that happened, because if you have QuickType in an automated build setting, your whole build chain depends on foo being foo and not purple foo. Okay, so that is that. So let's try again and see what we end up with here. So script, QuickType, -- lang, C++, and let's go with GitHub. Tests input JSON samples GitHub. And here we are. So as you can see, these names now look good the way they're supposed to. This is lowercase, this is uppercase, so it's all properly camel cased. And yeah, that was it. So stuff actually got simpler and it works better, which is always nice. So as I said, the next thing that we want to do is we want to put the types here. So we want to make these into actual struct declarations, but we don't know how to output types yet. So we have to implement that. And as always, we're going to go to Go, and we're just going to copy this thing, and then we're going to change it to make sense for C++. So we should put that here. So of course it's not called Go type anymore, it's CPP type. So I should explain. Type is a type in our intermediate representation. By the way, if you haven't read it yet, you should read the QuickType under the hood blog post on blog.quicktype.io where I explain how the intermediate representation works. And this is still written for PureScript, but the principles are exactly the same. So if you, this will make you understand a few weird things maybe that are not clear when you look at what we're doing here in TypeScript. Anyway, so we're back. So what this takes is, it takes a type in the intermediate representation and it produces a source like. So basically it returns something that can be transformed into source. We have this nice match type function, which means that we don't have to write a huge if for huge case statements. And instead we can write these individual lambdas here. And I should we talk about this yet? Okay, let's talk about this. So there are two cases where we can't really, actually I talked about this in episode 2. If you want to go back, I talked about how we're going to add annotations that help the user identify situations where we couldn't properly determine which type to use. And those are these two. So if you add these annotations, these will actually come out as warnings or issues when you run the command line client, and eventually it'll make its way into the web UI, but we don't have that implemented yet. And these two cases are the any type and the null type case. And I don't actually know which type we should represent this with in C++. I wonder whether we can just keep the original JSON in the produced types, which means that the user will have to then pry it apart and do whatever they want. So let's say we had some weird attribute that we don't know what to do with, and we declare it just as JSON. We call it weird. And then the person here we're going to make, so weird is going to be, I don't know, 5.6. And now what is that going to do if I run this? Interesting. It completely ignores the weird. So so this P should be, it has a JSON in weird, right? So then the JSON J doesn't contain a weird anymore, I'm assuming, because that's what's printed here. And then the person 2 has a weird, but what? Oh, it's null. Okay. So that, I'm sorry, I didn't convert it. Well, in that case, oh yeah, of course, we can totally do that. I just have to say j.add_weird. And this is weird, is p.weird. And let's see what happens. Let's run it again. Stop. Okay, yeah, so that's totally what we want. So this is basically the equivalent of we have no idea what this is the equivalent of dynamic typing, right? We have no idea what the weird is supposed to be, so we just declare it to be a JSON that is just not converted. So we just carry over the JSON and the user has to decide what to do with it, which is kind of nice, which is what we do in some languages where that's possible. For example, in Swift, we do that, Swift 4 in particular. but that was a lot of work. So I should include that annotation stuff. And then annotate it from source. Okay. So this is just going to be JSON, as we said, which means we don't know what type it is. So we're just going to let the user figure it out. I think bool is just bool in C++, right? Bool, be sure. Int64 is going to be int64t. Float is going to be double, or double is going to be double. String. Yes. std string. And I don't know whether that supports Unicode properly. We might have to figure something out later because we do need to support Unicode. Maybe we're going to make it an option to use non-Unicode, but by default, we should support Unicode, or a lot of tests are going to fail at least, and many people are not going to be happy. Okay, so arrays. For arrays, we should probably use the STL thing, which is STL vector, std vector, I'm guessing, std vector of t, right? Let's say of int abc. Okay, at least it doesn't, at least it takes it. So for this, for the array type, we actually get as an argument the type of the element of the array. And so in Go, it produces, if you look at this, in Go, it produces something like, let's make this true, false. So quooks here, as you can see, is an angle bracket bool, which is exactly what it says here, namely angle bracket, and then the converted type of the converted element type. But what we are producing is we are producing std vector off and then the element type. Okay, class type. A class type is really just the type of another struct. And here we come into trouble again with questions like, how do we actually want to represent this? We could just do containment in C++. So we could have, let's say we actually make the name. We make the name a string, first name and last name, right? And so this then would be the name, right? We could do it like this, which means that, oh, okay, I need that too. Which means that this is directly contained. So there's no indirection, it's not a pointer. So we're just going to do it this way, which means that we need the name of the class type, which is exactly what this type does. So the convenience renderer defines this method name for named type, and named types are classes and classes and unions. But we're not going to worry about unions yet. But this is pretty straightforward. So map is another thing. What is that called in C++? I think it's called map. Let's try that. So that would be std.map, right? So you have key and value. So it would be std string to int my map. Does that work? Looks good. Okay, so that's what we're doing. So it's std map from std string. And note that JSON objects always map from strings, right? So this is always what it's going to be. You can't have JSON maps that go from anything else. Okay, and for union types, we're just going to ignore this for now. We're not going to do anything about it because I don't want to explain it yet. We're going to come to it later. And usually this is what I do for implementing a new programming language. I implement everything except for unions first, and then a lot of test cases already work. And then you implement unions because they're often more work and they're kind of finicky. Okay, so we have the C++ type method now, so we can put it in here. And what we do is we just put it. Oh well, we need the type first. So what this gives us, this for each, is it gives us the JSON property name, and it gives us the name of the property in the generated code, but it doesn't give us the type. But luckily we have the class type, and the class type has a properties property, which is a map from the JSON property names to the types. So I can use that to say get JSON. So this is the property type. Property type. And now all I need to do is say this.cpp type of property type. And then I'm going to put in a space. And then we're going to put in the name. And then we're going to delete this. But we're also going to put in a semicolon. And as I said before, or as I noticed before, we need this semicolon at the end of the struct, which our emit block doesn't do yet. But I assume that we're going to need a emit block for other stuff too, like for maybe if statements or something. So which don't need that semicolon. So we're going to add an argument with semicolon. I think I have that with, do I have that with C#? Anyway, add semicolon, boolean, and emit line, whatever. If with semicolon, then the emit line is going to be with a semicolon. Like that. And here it's complaining that something is wrong. Yes, of course, because we need to pass that argument. Where is it? Emit block with semicolon, true. So there. Now let's take a look at this. We should now get nice, proper struct declarations. Oh. Okay. So these are the. Let's look at the output first. So this looks fine, as far as I can see. We have a lot of cases where, oh, fix me. Really? There's, right. Okay, I'm going to talk about that. But yeah, apart from these fix me's, there's a lot of fix me's here. Apart from these fix me's, it looks great. And as you can see, we sometimes have cases where we have this thing here, this JSON thing, and it really does give us these warnings here. So for example, it says, quicktype cannot infer this type because there is no data about it in the input assignees. And that's actually true. It's always an empty array. So these fixmes, if you look at the code that we generate for GitHub in, let's say, Go, GitHub events, you will see that coming back here, for example, in milestone, there's due on. So let's look at milestone. Due on. So it says optional here, but it's not a weird union type. It's just a pointer to a string. And the reason for that is that sometimes in the input, this property is either missing or it's null, which means that it can either be a string or it can be null, which means it's a union type. So it's a union between string and null, which in many programming languages we can represent with some form of an option type, of an optional type. In Go, it can be a pointer. So the pointer can be null or it can point to a string. In C#, it's optional by default because strings are reference types, so we don't even need to change anything. In C++, I don't know what we're going to do. So I'm going to do some Googling. And after some Googling and trial and error, we're back. And I think I figured out how to do it in a somewhat nice way. So it turns out that in C++ 17, there's an optional type, but I don't think most people use C++ 17 yet. And there's an optional type in Boost, but I don't want to depend on that. So we're going to use unique pointer, which can be null. And this is how it works. You declare a unique pointer to an integer, for example, and you can check by converting it to a Boolean whether it's null or not. And if it's null, you can if it's not right, if it's null, you can put JSON null in there. Otherwise, you dereference it and you get the integer. And to go the other way, you have to check the JSON for null, and then you would just assign the null pointer. Or you have to assign the unique pointer, which requires allocating a heap object, which is an obvious downside, but that's just what it is. So let's put that into action. So we actually do have to handle at least one union case here. And if you look at how that looks in Go, is we have this function nullable from union, which returns a type if the union is a union between null and only that type. So for example, if the union is string or null, it will return the string type. If it's int or null, it will return the int type. But if it's a union that either doesn't contain null or that contains null and more than one type, so null or int or string, it will return null, which is kind of confusing, but it won't return a type. Let's put it that way. Which is exactly what we want. And we're going to handle the case where it does return a type, and the case where it does not return a type, we're not going to handle yet, because those are more complex unions that we're going to have to declare a struct for, or maybe a union for. I don't know how to do it yet. So let's just copy that. So if we don't get a type, no, if we do get a type, let's say if we don't get a type, nullable, if we don't get a type, we return the fix me again. But that should not be the case, at least in the GitHub example. And if it is nullable, then we can return a unique pointer. So we return an std unique putra, and the type, or the type that is being pointed to, is the CPP type of the nullable. So for example, if this is a nullable string, so it's string or null, then we will get a unique pointer to a string. And that is that. So let's try that. So as you can see, we had milestone was due on, for example, and actually a lot of them in issue. We had lots of them in issue. So let's run again. And I don't see any fix me's. Let's look at issue. So here, for example, closed at, it's a unique pointer to a string. Milestone, again, is optional. The pull request is optional. So there, we got our structs, and we even have the semicolon at the end. So I think I'm gonna close it here for now, and in the next episode, we will actually really implement this to JSON and from JSON, which should enable us to, for the first time, serialize and deserialize some actual JSON in C++ with the code that we generated. So I'll see you then. Bye.